线上有多少人？好，大家上午好。然后我们接下来开始下半场的这个报告。我们下半场我们自己好像都是中国人，所以我就用中文来主持。所以我们下半场的这个报告呢，主要有3位演讲人。然后呢，我们第一个报告是关于这个氮化镓集权的驱动下一代电源系统。那么演讲人是Tony 刘，来自于 Navitas。那么我们请刘博士啊，请给我们开始演讲。
All right. The topic of my talk today is GaN integration drives next generation power systems, and the contents of my presentation. First of all, I will start with a simple introduction to the GaN power system, and how to sort through the mainstream solutions to the GaN industry. And following that, I'm going to spend a little bit of time, dive deep, talk about what is the main challenges in the GaN integration solutions versus the discrete solutions. And after that, we'll probably spend a bit of time focus on what we have done here in Navitas in terms of integrated drive GaN ICs. And finally, wrap up with a simple, quick summary. So that's the main content. I think this is probably very familiar to most of the audience here and also the audience online. I think most of the people have seen this before. Among some people, among all the major commercialized semiconductor materials, and we have, for example, silicon carbon and carbon nitride. Gallium nitride so far has the best semiconductor parameters in terms of breakdown, critical field, saturation velocity, electromobility, etc. Now, what that's supposed to mean? For example, give me 1 second, so I need pumps. For example, the GaN here has the largest breakdown critical field. That means we can actually use relatively small geometry, like small devices, to achieve the same kind of voltage rating. And for the drift velocity and electromobility, both of them means GaN naturally can switch in faster. Those are really the natural advantages of GaN compared to traditional silicon. And this is probably very known for most of the audience, so I'm not going to do that too much about it. If you look at GaN solutions nowadays, I'm talking about the mainstream industry solutions. We can divide the GaN solution into 2 categories. The first one is, of course, the eMode, like enhanced GaN devices. Another approach is depletion mode, and normally we call it D-mode. If you look at the D-mode itself, for example, the D-mode itself, by itself, because the power FET itself is continues on until you apply an active voltage. What that's supposed to mean? It means by itself, it cannot really be used for power supply system itself. So what do we do? How do we address these challenges in mainstream industry? And we have 2 solutions. And the first one, and it's probably the most widely used approach, is cascade approach. I think you probably have seen some of those in the past 3 days presentations. Meaning we have this D-mode power FET, and we put a low voltage silicon FET in series. We call it the cascade devices. You control the whole power effect by controlling the silicon FET itself. Will this work or not? Of course, it will work well, right? But what I'm going to say probably maybe will offend some of the audience here, maybe, and also online. Personally, I never believe this is the final solution of the GaN system. As a transition period of solution, it works fine. Of course, no doubt about it. I just don't feel like this should be our final destination. Why is that? Here's my arguments. If you want to use a GaN, why we're using GaN? Like I said, because GaN by nature itself, it has like, high switching frequency, less switching loss, less QG, barely, like nearly zero recovery energy, for example. Now, when you put like a low voltage silicon FET to it, right? When you insert a silicon FET to it, essentially you degrade the whole power system's performance by introducing larger QG, and also because it introduced the body diode itself, you increase the reverse recovery, etc. So you sort of like, not really using the full benefit of the GaN itself. So that's why I never really fully believe this is our final solution of this. And plus, and since you have the two power in series, right? You have this high power eMode effect there. At the same time, you have this low voltage silicon FET here. To achieve the same RDS zone, namely you have to put a larger die, a lower RDS zone, high power eMode effect there, and therefore increase the total solution cost. So personally, I never really liked this kind of solution, and also Navitas didn't pick this solution at all. Does that have the advantage? Of course it does. Like I said, it definitely works because eventually you're really driving the whole system by driving like silicon FETs. So naturally it's more compatible with existing silicon drive, but people love it. So you can basically drop in a good place. And compared to like traditional all silicon power FET, it still has a huge advantage in terms of with switching loss, etc. So it does has a value. We just don't believe this is our final destination of this solution. As a transition period, it works totally fine. No problem about that. Another solution in the mainstream industry of the eMode GaN solution is direct driving eMode GaN. How do we do that? Well, you have the demo, right? And to make it work, instead of inserting a silicon low voltage silicon FET, what we decided to do is, well, we can put another silicon driver, put like a negative voltage drive it directly, because you can need like a negative gate voltage to provide a negative voltage to turn it off. Will that work? Yes, it does. The problem or challenge of this one is, meaning like you have to put a very complex negative voltage gate driver there, and that makes the whole system a hell more complex than the traditional, eMode driver systems. I guess that's probably part of the reason that this hasn't been really adopted as a mainstream solution. Other than eMode, another approach, probably most widely used approach so far is the eMode GaN solution. Now, if you look at the eMode structures, and there are two major solutions we're talking about. On the left side, what we usually call it recessed gates. And if you look at the one, the key here is the gate structure. Sort of like you can simply put like we ditch a trench as an organ layer, like eat a little bit area and material away. Another approach, that's what we do here at Navitas, and some other companies also use some approach like this. Your gate structure, the P-GaN, it basically sits above this organ layer. Both approaches have its pros and cons, I have to say. On the left side, technically speaking, and when you ditch a trench of the organ layer, you have this potential to really, increase the threshold voltage of it. It's a really welcome feature because once you have this higher VTH, you could achieve a high noise immunity and put this whole system design a lot more, attractive. However, the challenge is we are really talking about several nanometer of material here. So it's really challenging for process control, especially we're talking about the mass production, shipping like millions of parts. How to control the process and get a very, very tight uniformity and variation, it's really challenging. Navitas on the other side picked the right side one because we believe this is sort of like the well-balanced structure at this moment, given our process status. Okay, so what we just talked about is literally just several mainstream solutions to the GaN industry. eMode, of course, apparently is what we believe, it's probably the most readable and immediate solution for the industry. But one major challenge in this eMode GaN solution is, we slides here, I'm not sure it's readable. Now this graph here showing here, now the x-axis is the gate voltage, and the y-axis is the predict lifetime, or you can talk about reliability. It's a conceptual drawing, it's not really like, mathematical correction or something like that. And here the same, unlike silicon, GaN device generally require gate voltage to reach 6 volt or above to really get the GaN device's saturation current and RDS reach to the really sweet spot of that. But here's the thing. GaN's reliability heavily degraded when the VG, for example, increased to 8 volts or above. And sometimes, even you go to the voltage of 8 volt or even less, the GaN's gate is starting, seeing some stress. So this is the reason that the GaN device is very hard to use as a discrete. I know some of the audience online or in this room may ask us some question. Well, what about silicon? We have been using PMOS for decades, and it was totally fun. It is fun. I agree with that. But here the same. In the PMOS or traditional silicon, well, gate threshold, for example, you have 3 to 4 or something like that. But at the same time, the gate not going to break down until the gate can reach to 20 or something. Now, when you use the silicon PMOS and put in the volt level and just use it as a pure discrete, you basically have like a 10 volt or large, even more room to really play around. Even you have like a really crappy, lousy PCB board design, your device is not likely to break down right away. Here in GaN industry, it's a totally different story, like I said, because you need the gate to reach 6 volts. Yet, once you get to 8 volt, the GaN starts to break down. You literally have only like 1 to 2 volt kind of room to play. That's why this GaN, to make it work, is really challenging. I'm not sure whether the audience here or online knows this. Actually, there are some pioneer work in industry and pushing this GaN VGS to high voltage, and we have seen some pioneer research work to even high voltage like 10 volt or above. However, at this moment, I have to say, so far, nothing is quite really mature yet to really reach it to mass production level. So in the short term, I still predict that, I still expect that this is sort of still the status quo for quite some time. And because of this, we believe to address this one, we need to do something different rather than discrete, although it's not easy. Now, following that topic, I think that most of people probably know that in the current GaN industry, a lot of companies might be using discrete or co-pack. If you use GaN as a pure discrete, meaning like your power FET is mainly a standalone device, your gate is exposed at a package level, right? It's explosive pin, everybody sees it. Or you can put it as a co-pack, meaning like you have a main power FET. At the same time, you put a silicon driver, put them together in a single package. But if you do it that way, well, your GaN's main gate is still exposed. It's just not on the whole package level, but it's still inside, right? People can still it. People don't see it, but you know that. And the silicon die and main GaN die still have this bonding wire structure. So that's one approach. We will call that discrete or co-pack, whatever we call that. Another approach is the way Navitas have been chosen, which is integrated solution. And the driver we actually did was mainly put on the GaN itself, meaning like the driver and the main power FET and the GaN will sit on the same die. So the gate of the power FET GaN device itself is never going to sit at the die edge. So that's the big difference. And what's the benefit that we were looking at? Well, here's the thing. And most of what is here probably here was like AE background. You probably know this. If you have this main power FET shown here, now I'm showing here is like yellow as a main power FET. If you have like a pure discrete again, right? You have like a silicon drive or something on the external world, then you definitely have some PCB trees in between. And we all know that. That will generate a hell of plastics. Plastic inductance, particular capacitance, you name it. And if it's a co-pack, you have a GaN die here, you have a silicon die here, and this then will be like, bonding wire. Again, there will be still plastic in this loop. If you break down, not a lot of characteristics, not only like gate driver loop, and also like a pod loop as well. And what that's supposed to mean? That means, let me show you one slide. Here on the right side, if you can see it, it's a little typical. I mean, I'm being a little list this application per se, but it's a little typical. And I guess most people have seen this before. When you're using the GaN as a pure discrete, because the parasitic exists on the parasitic, it's easily to say like a several volts of the overshoot and several volts of undershoot, all because of the parasitic, in loop inductance, etc. On the lower side, the green curve, you will see this are Navitas GaN IC. When you put that gate driver inside of the die, you will see very clean, barely not noticeable overshoots and undershoot. That makes a huge difference. And like I said, that 2 volts overshoot or 4 volt undershoot could potentially damage these gate devices in the long run. And we have many other tests as well. For example, when we put this pure discrete as a high spectral frequency, we also see a lot of noises from VGS, switch noise, etc. And that really causes collisions as well. Sometimes it comes to the VGS as well. This is very challenging to address because all those kind of complicated elements eventually would lead to poor EMI performance and also device failure. And if you look at the right side, the Navitas is the integrated solution, and you would always see very clean switching waveform. Now people would argue, well, yes, I still want to use the discrete. Can we do something on the board level and to eliminate this or suppress this? For example, by instead of some, let's say, gate resistors, damper resistors to do this way. Can we do that? Of course we can do that. As a matter of fact, it's been widely used in the industry. I mean, almost everybody uses it nowadays. But the message we want to deliver is here. Now, I'm putting some waveforms showing here. On the top side is the discrete solution with external damper resistor, and on the bottom side is our Navitas is a monolithic GaN driver and FET solution. Now, if you look at the waveform, you will see here is the green one is the VDS, the red one is the VGS. But instead of this damper resistor, it does help to suppress the learning itself, but not really completely get rid of it. And you could argue, we can keep increasing that resistor to a very large amount of value. We can do that, but then you would suffer the efficiency loss. Now, if you do the comparison, look at the bottom side is a Navitas solution, you would say, we don't really have to add any extra, gate resistor to do anything about it. And at the same time, you could actually really clean switching waveform. Meaning you don't have to suffer any efficient loss while achieve the long-term reliability. So that's one big major difference. And what I was just showing here was actually sort of like a low to medium markets. As you guys probably aware, most of the applications nowadays GaN has been doing is really compare the low to medium markets, low to medium and power domains. And we are getting to like a high power applications, some of the field applications such as EV, data center, etc. And we have lots of sessions in these meetings talking about kilowatt, etc. Now the message is also very clear. What we're seeing here is if you have like RDS on to, for example, tens of million water, and the current pushed up to like hundreds of amp, that overshoot is even more so. And in our simulation on our bench, we have seen, I'm talking about like if you do any protection whatsoever there, the overshoot and undershoot could easily reach to like tens of volts or even 20-something volts. That is very dangerous for GaN devices. Of course, you can argue, we can add a full-blown protection to it. You can do that, but then it will make the whole solution very hard to use because you add a lot of extra costs, right, to the whole systems. So what we're trying to see here is, you want this GaN to make it work. GaN is different, compared to the silicon. You want it to work, it's better to address these gates, very narrow gate as a range and comfortable zone. And to do that, we believe gate driver integrated one is the solution. It's the hardest way, yet it's the fundamental way to address this question. As a matter of fact, in the past several years, and ever since Navitas released the first commercial products, we have been doing a lot of things, to improve our driver. The first one I'm talking about today is actually the Navitas patent integrated 10-ohm DVD control. We have been using this for like a couple of years. We have this very fancy multiple phase gate shifting control. while the slow phase in the gate turn-on phase, we could actually turn from external world by just the external RDD resistor. And the benefit of that one can achieve relatively good EMI, while at the same time barely sacrifice any efficiency loss whatsoever. And here in 2022, early this year, we just released our generation 4 Navitas product line. We call it NV613XC family. And for the first time, we introduced Navitas patent integrated turn-off the IDD control. Again, we also introduced this multiple phase turn-off the IDD control to it. And I'm not sure, I probably have to apologize because this graph doesn't seem like very readable. But the message what I want to deliver is, and we have noticed that the EMI performance improvements from the traditional turn-off the IDD control to the new IDD driver with this turn-off control. The EMI performance improvements we see typically to like 5 dB to 10 dB from mid to high frequency band. It's very noticeable and very steady. And the best of it, we don't really introduce any efficiency loss at all. So we just talked about how to handle these gate voltage SOA stresses by integrate the gate driver. As a matter of fact, Navitas not only has been done things, for example, to the gate driver itself. In the several years passing by, we have been doing a lot of things by adding new features into this GaN IC. From the early simple driver to what we have done today, I believe I sent you directly yesterday. Lenovo just announced this Navitas new generation GaNFast hardware, which I believe that's sort of like showcase what we really have achieved so far. A lot of new features has been added to this GaN IC. The first one I want to talk about is actually most popular. One of the most popular features from Navitas products is called lossless current sensing. We patent it. Shown here is the typical waveform of this lossless current sensing, working at both DCM and CCM modes, around like 200 kilohertz. You can see from the waveform. The yellow one is the current sensor voltage sensing, and the green one is the current waveform. You can see those two are almost tracking simultaneously, like real time, and very high accuracy and a faster response. And people may ask, why do you have to do this lossless current sensing? Here's the thing. And compared to traditional approaches, like if you don't do this way, you really have to put like sensor resistor external load. Like for example, like you have like RDS on 170 milliohm, for example, you insert another sensor resistor externally. What we noticed that is the system hot spot in terms of temperature. By introducing this current sensor feature, we can really reduce the total system's temperature to almost like 10 Celsius degree cooler. It's very noticeable. At the same time, we also noticed that it being across all product line like that, by introducing this current sensing, it actually could boost the efficiency to roughly about 0.5%. Very noticeable. Very noticeable and a very welcome thing. Again, now this feature, to be honest, you cannot really achieve it if you cannot do anything about GaN itself. Like you can only do a silicon driver and put that main part of the GaN together with it. There's no way, period, you can do any current sense losslessly. It's plain and simple. And this is something like Navitas has achieved and we patent it. Another feature our product has been, utilizing is we call like automatic OCP, overcurrent protection. Now on the left side is the traditional discrete GaN. Of course, you can put like a controller or something like that, and put sensor resistors and sensor current, and then do the overcurrent protection. With the current reach to a very dangerous zone, you decide to shut down it. Will that work? I believe so. But here's a catch. Because you really have to pass that information, right, to the silicon driver, to the controller. There's this very, very long signal chain. When you decide to shut down the FET, you have to pass that signal back. And generally, that kind of delay, we're talking about like roughly about 200 nanosecond order. Here in Navitas, this OCP, we'll call it like a short circuit protection, we built them in GaN itself. So meaning like protection can happen right away. That reduces this, approaches from 200 nanoseconds literally to 1 order, 30 nanoseconds, or even less if you really want to. Some other features, I'm not really going to jump into too much details because of limited time, for example, the OTP. This, again, it's also some of the features that Navitas has been doing. Again, if you don't, for example, if you do a pure discrete, you don't really have the ability to really sense the GaN device temperature. Where by doing this GaN IC, you do know what temperature it reaches, right? And then once it reaches to a dangerous zone, we can shut down right away. We'll do something, control about it. Also, standby mode. This is a very popular feature for example. And we know that when the PWM stays quite a certain time, we put this system in standby mode, therefore reduce the power consumption. I'm not going to go through one by one of some of the features, and especially the half bridge, because as a matter of fact, actually, I think our senior director Lenovo just yesterday announced this half bridge. And quickly summarize, and by putting half bridge into integration IC, we literally put a lot of things inside of the die. For example, you integrate a boot driver, integrate the lever shifters, and boot diode, and 10-on 10-off control, short circuit correction, OTP, etc. A bunch of things, and could save this whole system cost by significant portion. We're talking about 5 times on your component reduction with a hell lot of cost reduction. I guess I probably have to jump to the, quickly to the summary. The first message I want to deliver to this audience is, personally, I believe every part of it, seriously, and every single cell of me believe GaN has a very, very bright future. That's the message I want to deliver. Personally, I think GaN is the next generation part of semiconductor that offers the superb performance, no doubt about it. I mean, there will be probably decades of, prime time of the GaN industry yet to come. Of course, it requires the audience here and online to really work together. But the future is very bright. And another message I really want to deliver here today is, we believe for the GaN device to really work, it requires an integrated driver and capacity to really achieve this high performance and reliability. It's really the key. Until one day, for example, our GaN device can really handle this very high voltage stress. In the short amount of time, I believe this is still the key for the solution. And then the last point I want to deliver is, we believe here in Navitas that by putting extra integration to some current sense, real-time protection, OCP, etc., things like that, we could achieve better performance, highest efficiency and reliability, and it's a really welcome features and added on to this whole system. So that's sort of wrap up my talk today. I guess I'll probably leave some time for the Q&A. Thank you.
OK， 非常感谢。So 你们谁有问题？各位，我们线下的各位老师有没有问题 ？OK， 我们线上的有没有问题？ I have a question about your current sensing, about lossless current sensing. So, could you give us more introduction about the basic principle of that? I don't know whether it can be, but if it can, please give us a detailed introduction about the lossless current sensing.
Yeah, absolutely. Unfortunately, I can't really show too much details of this one, but I think the basic idea is probably okay. I mean, the principle is really simple, let's put it this way. Like if you do what current sensing, like lossless way, and the most widely used lossless current sensing, you can think about it, it's more of like, you do a replica, mirror it, take a small portion of it, and then measure the current, right? And you know how much current flow to that small replica, and then you know the whole current flows to the main part of it. That's literally the idea of it. You can think about the current mirror about it. It's just like, to really make it work in GaN, we have to do something differently. Just, rather than just a simple mirror. Because if you simply mirror it, you will actually see a very high voltage signal out of it, and you want to send to the silicon side. where most of the silicon driver cannot really handle high voltage stress. Most of it is a low voltage gate driver, for example. So we have to do something special there. But the idea is simple. You can treat it as like a current mirror.
Okay, thank you very much. 有没有什么问题？其他的 ？OK，那让我们再次感谢他们一位，谢谢。